All right, let's get rolling. So last time we were talking about CPUs and the various different cores. And we talked about a couple of different processors at the very, very high level. So one of the things that we kind of mentioned is, you know, our physical size of our processors has not necessarily drastically changed over the years. But what has changed is the amount of stuff we can fit in that same space. We keep getting better and better and better at putting circuitry closer and closer together, with the enemy being, among other things, heat dissipation. And now if we think about, that's the original problem with processors in general, whether we're desktop or laptop or whatever. And then on top of that, we consider the desire for mobile to be, quiet, to be silent, to not burn your lap. If you're thinking about a laptop, things like that. So we have a lot of desires as it relates to mobile devices that are in direct conflict with faster and faster and faster processors. Yet we want that too. We want both of those things. We want our processors to be super, super, super fast. We want them to be super cool, super silent, super. We don't want to have fans inside of our computer going super fast to have everything cooled off. And where's that hot air going to blow? Is it blowing off onto our leg? Is it making the room that we're in heat up? Yada, 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 all this stuff. Okay, that's in direct conflict with our end user experience and what we think we want. And that's kind of the kicker here, is what we think we want. As a normal consumer, we think that we want everything to be top speed, where at the end of the day, what we really need is we want our end user experience to feel like everything happens as fast as it possibly could happen relative to what we are currently doing. And it is just a fact that many, if not most, operations that a computer does do not require significantly fast processing power relative to what's possible. Now, every now and then you're doing something that does require, some extra heavy lifting, playing a video game, something like that, that's going to tax the processor a lot more than something like checking your email. So you do want your processor to have the capability of ramping up to a higher performance mode if necessary. But in terms of general use mode, you want it quiet, you want it not getting hot, and you want it to be fast enough so that you wouldn't notice the difference between a faster processor not being taxed and a slower processor running at full speed, keeping up with that faster processor that's barely having to work. All right, so I have mentioned here, starting here, multi-core trade-offs. So we have a couple of different things. I'm actually going to insert another slide here. And actually what I'm going to do is, just so we have an actual example to operate off of. Sure, everybody in so far. Let's go with iOS, and let's go iPhone processors. Get back to that list so I can pick one of them where it brings in the secondary core. All right, let's look at a A12X. For high performance, for high efficiency. Okay, I think this one will. Let me get a picture of this guy in here. No, it doesn't matter. We can just operate off of this spec sheet. All right, so we were looking at some of this stuff last time, but I just want to bring some attention to this piece right here, where we're talking about the various processing power that's inside of this processor. So we have 4 high performance CPUs. So this is going to be, no, at this point, we're getting to a pretty hefty, I mean, these mobile processors are getting pretty close to what we have in desktop processors in terms of at a glance abilities. Go ahead. Oh, so not muted. Okay. So we have our four high performance CPUs, but then we have 4 high efficiency CPUs. So these are going to be slower performance, less heat, but probably fast enough for a majority of what we're going to do. So I would say it's more than likely that a high percentage of the time, 95 to 99% of the time, you're only going to be using these high efficiency cores, which is going to give you longer battery life, which is going to give you less heat, which is going to give you adequate performance, all that stuff. Okay. So when we have multi-core in the first place, we're really talking about 2 separate things. Multi-core, we're talking about a processor that has multiple individual cores, and we're not talking about the specs of each of those cores, versus having cores of different performances. One thing we need to start off with as multi-core trade-offs is the OS is more complex as we get more cores. The OS has to schedule processes to be done on those cores. Not all processes happen at the same time. Now, we're not focused on the operating system side of things here, so we're not going to get into that too much, but we still want to think about it as being a fact that the software that's running our computer, that operating system, becomes a more complicated piece of software as we're having to manage more resources on our computer. And this class is about the resources. That's what we care about. And one of those resources is the processor. And what makes that more complicated is what's inside the processor. And if we look back at this picture, we're seeing, that this guy's got some pretty, crazy specs, and he's from 2018. So we have eight cores on the processor, 4 high performance, 4 efficiency. We have 7 GPU cores, so that's our graphics card. And then we have these neural engine cores that are done for machine learning stuff. Just a separate piece of processing power for that kind of stuff. So in order to take advantage of all those things, the operating system needs to be aware of it. All right, we'll talk more about that. But those are trade-offs of having multi-core. More cores also means more electricity. So less battery life. Or requiring I'm going to put in quotes here, better battery. Better can mean larger, better could be in a new technology that doesn't drain as quickly, all sorts of things like that. All right, so kind of our punchline here is more cores doesn't necessarily mean better. An 8-core processor isn't necessarily better than a 4-core processor. It's going to depend on what you're going to be using that processor to do. The old adage for gamers was you would rather have fewer cores that ran faster than more cores that ran slower. So a dual core or a quad core processor that could operate at the fastest number of gigahertz, let's say, was preferred for a PC video game player over a 8 or 12 core that had a slower, slightly slower clock speed, because you weren't going to take full advantage of that. And since you were mostly using that machine for playing games, you were more than likely going to be pushing your processor's computation power. So you wanted to be as fast as possible, and you were willing to give up some extra cores because the OS is more complex and scheduling for more cores is difficult. And really, it's pretty common that not all processes can happen at the same time anyways. So if you have 8 cores, there's a good chance that some of them are going to be sitting there completely idle a good percentage of the time. Not really helpful. All right, so let's kind of keep going down the rabbit hole here. And we're talking about the resources of our computers. And
excuse me, Professor Littman, I have a question dealing with the multi-core processor.
Sure, go ahead.
So, are those trade-offs exclusive to the RISC set of instructions like with ARM, or is that for both types?
It would be both.
Okay.
Yeah, I mean, you might be able to argue that maybe the trade-offs, well, I don't think you can say that the trade-offs are necessarily better or worse when it comes to ARM architecture versus like Intel architecture.
Yeah.
That's kind of a different argument. We'll talk about those things, but I think it has more to do with the type of use for the processor.
Okay.
All right, so going down the rabbit hole to more of our resources, we want to think about our hard drives, or you can, if you want to consider this is our long-term storage. You know, so when you buy a phone and the phone has 128 gigabytes or 256 gigabytes or 512 gigabytes of storage on it, and some are expandable where you can put an SD card in there and give you some extra space that may or may not be as high performance. But when you're talking about long-term storage, a lot of times you're not necessarily all that concerned about speed, but we're going to talk about that here too. Excuse me. Okay. Now we're going to talk about a couple of things in here that don't really apply to our mobile devices anymore, but we'll still mention it because it kind of tells the story for us. So when you're first buying a phone, you know, iPhone or Android device, whatever, you know, one of the things kind of our common uses today might be music, right? You know, and also pictures. I guess maybe pictures is even the bigger thing, because pictures, as our phones come with these better and better cameras, the physical storage size of each of our pictures we're taking keeps getting bigger and bigger and bigger. Well, now we need more storage to hold all our pictures. And you know, with social media, we're taking pictures of everything, right? I take pictures almost every piece of food I have on a plate in front of me just because I do. You know, and some of you travel, you take pictures of everywhere you go and all that stuff. So you need that capacity for storing stuff on your device. And then on top of that, you're also paying for cloud storage. So the things get backed up in the cloud in case your phone gets lost or stolen, or you switch to a new phone, whatever it is. All right. So one thing we care about is total capacity. Now, don't necessarily assume that a 512 gigabytes of storage is better than 128 gigabytes of storage. Better, put that in quotes, really depends on what you're looking for. Sure, if it doesn't mean, if the speed of the storage isn't important and it's just capacity, 512 gigabytes is better. You can hold more pictures. Anyway you cut it, you can hold more pictures in 512 gigabytes than you can in 128 gigabytes. But if you're going to be using that storage for moving things quickly in and out of memory, you want higher performance storage, not necessarily higher capacity storage. So I make a kind of an argument for that. And this is something where you might see more on a laptop type argument. And I like to bring things always back to kind of how consumers view things. This is probably becoming less and less of a thing these days because now pretty much all of our computers have gone to solid state drives. But up to even just a couple of years ago, you might be looking at a new computer online, a laptop, let's say, and as you're going through and you're configuring it with how much memory you want and the hard drive and stuff like that, you may have seen that a computer came with a 1 terabyte HDD. So this is a hard drive, but it's a mechanical hard drive. Okay, so an HDD is something where there's physical disks spinning inside of the computer, as opposed to our cache-based memory today, which you did a paper on, our solid state stuff. All right. So now those mechanical drives, the HDDs, they came in a couple of flavors. You know, you could have a 5,400 RPM or a 7,200 RPM. There were ones that were 10,000 or even 15,000 RPM. But typically in laptops, it was 5,400 was your default and 7,200 was like your upgraded one. And the idea here is the faster that it spins, faster the RPMs, the faster the access time that it took to get to your data. Okay. Now, so what was interesting is like I just mentioned that, and in this example, we're talking about a 1 terabyte hard drive. You might, maybe the default for the laptop is a 1 terabyte hard drive, yet you could upgrade your hard drive. Maybe you pay $400 extra and cut the size in half. You can upgrade your 1 terabyte drive to a 500 gigabyte solid state drive. Okay. So now to the average consumer, they look at that and they say, okay, I'm getting half the storage and I'm paying you more money for it. They're not considering the technology difference between an HDD and an SSD. All right. So I have an image on our a couple slides later, I think. Let me jump this here. So we just talked about capacity. When we talk about performance and we're talking about solid state drives versus hard drives, you know, obviously, and this cost is even different now. This is a little bit dated. But you know, if you just operate off of this, a solid state drive might be 3 to 4 times the price of a mechanical hard drive. Now they've come down where it's hard to buy mechanical hard drives, but if you do buy a mechanical hard drive for like a desktop server, they're really cheap. So this is probably still relatively true where solid state is more expensive, but solid state drives are not prohibitively expensive now until you get to the larger capacity. Like for instance, a 256 gigabyte solid state drive to a 512 is not a big jump. A 1 terabyte is probably a bigger jump. Maybe going from 1 to 2 terabytes has a more costly jump for solid state right now, but the price keeps coming further and further down, and it's already not overly expensive. All right. But, you know, realistically, in our discussion right here, we don't really care about cost and capacity. We're really focused on performance here. So one concept here is latency. What's the search time, the seek time? And I was just mentioning that with those RPMs and those mechanical hard drives. So a mechanical hard drive has an average seek time of 12 milliseconds. So from a human perspective, that's pretty fast. But notice here that a solid state drive has a seek time that is 100 times faster, 0.12 milliseconds, 100 times faster. So it can go and find stuff on the hard drive 100 times faster on a solid state drive than a mechanical hard drive. You're going to feel that when you're using your computer. One thing I tell people, if you're running like a desktop computer, as long as you feel like you have an adequate amount of RAM and you want your computer to feel faster, and you're running a hard drive, HDD, very first thing to replace is the HDD with a solid state drive. You'll immediately notice a drastic improvement in performance. The machine will feel a lot faster. Solid state drives are like a Ferrari, where mechanical hard drives are like a bicycle, something like that. All right, so that's seek time. That's looking up what you want and then moving data, you know, call it 4 times. A solid state drive can move data at 4 times the speed of a mechanical hard drive. It's actually probably a bigger gap than that now. Our technology for solid state drives keeps getting better and better and better, and we can move data even quicker than that. Look at this random access for data. So now we have 125 megabytes versus 2 megabytes per second. Drastic speed difference. So in every single category here from performance, solid state drives blow a mechanical hard drive out of the water. And then you keep going down with some of our decision making related to mobile, and you have solid state drives use half the amount of electricity that a mechanical hard drive does, and that's probably going down. They're also silent versus there's some noise to a spinning hard drive, and they last twice as long in terms of the life expectancy. So everything about an SSD sounds better. It's faster, it's big enough, it uses less battery life, it's silent, and it'll last longer. Not a whole lot of reason to look at a mechanical hard drive any longer. Okay, so this next chart here just talks about the conversion chart for bits and bytes. So when I say things like 128 gigabytes and things like that, you should be able to kind of move between these. So study this if you haven't been exposed to this stuff before. So if I say 128 gigabytes, 128 times 8, that's 1024 gigabits. That gets me over to this other column. And if I want to say 1028 gigabytes, 128 gigabytes times 1024, that gets me to 131,072 megabytes going up this. So we multiply by 1024 as we go up, and we multiply by 8 as we jump to the other side to get the bits. There's going to be more bits than bytes in something because there's 8 bits to every 1 byte. So be able to do the math in here, but really most of the things we talk about over on this side, we talk about bits, kilobits, megabits, gigabits, terabits. These are things that we don't really talk about very much, with the exception of megabits is used when we're talking about the speed of an internet connection, which is why it's misleading for consumers. So when you buy internet at your home, you might have a 200 megabit per second internet connection, where the average consumer thinks they're actually talking about the megabyte thing over here. And a lot of the TV commercials further lie to you by, they don't even say megabit or megabyte. They just call it a 200 meg internet. So now you don't even know which thing they're talking about. But that's really the only example anymore that we might use bits on this side, other than just the standard bits for zeros and ones, because that's what digital hardware stores, and that's what we're going to care about in here is the bits. But for larger pieces of storage, we typically refer to them by their kilobytes, megabytes, gigabytes, or terabytes. So understand how those math problems kind of work. All right, I have a picture here. So I say, how should you think about a computer? And and for us in here, we're thinking about mobile devices, but whether it's a big computer or a small computer, this idea is the same. You can look at the motherboard of a computer, and you can say this looks kind of like a map of a country with all these interconnected roads, and you have these main points of interest. Those are our resources. So you have your processor, that's a main point of interest, and a bunch of roads go to that processor. And then you have your system memory, and there's a bunch of roads that go there. So, when I mentioned memory is kind of like a toll booth, where not all toll booths are created equal. So sometimes you got to pay a little bit more in terms of time to get through a particular toll booth, because some memory is faster or slower than other memory. A good rule of thumb is the smaller the memory and the closer it is to the processor, the faster it will be, and probably the more expensive it will be per bit. If you really drop it down to, the cost per bit for memory. And we'll kind of talk about some of those options, but generally when we talk about what's the fastest memory inside of a computer, that fastest memory is going to be something called a hardware register. which is memory that lives right on the CPU. And that's going to be super, super, super fast, super, super, super small capacity. We're talking it's going to be like 8 bits, 16 bits, 32 bits, 64 bits. So very small capacity. It's holding like a single value. But the speed at which it can operate on that value is very, very, very fast. But the cost of that memory per bit of storage will be significantly higher than like the cost of storage on like a solid state drive, even though we wouldn't necessarily view it as prohibitively expensive anymore when you talk about the cost of a processor. So just something to kind of keep in mind, but if you did drop it down to the bit level, you would notice. All right, so when we think about cost of memory without getting into the cost per bit, but like I mentioned, hardware registers are going to be the fastest and most expensive, followed by cache memory. And actually within cache memory, we have multiple different, we have L1, L2, L3 cache. So L1 and L2 cache is cache that is involved with a single core of the CPU. So that means if you have 4 cores, you're going to have 4 different L1 and L2 caches, one for each of those cores. L3 cache is shared between cores. So it allows you to do kind of inter-core communication when the operating system is having to manage what processes are living on what cores and how do we get data from one to another and that kind of stuff. Okay. And L1 cache is closer to the CPU than L2, which is closer to the CPU than L3, which is farther from the CPU than hardware registers. All of these are closer to the CPU than our system memory. So our system memory is going to be like when you buy a laptop, it has 8 gigabytes of RAM, 16 gigabytes of RAM, 32 gigabytes of RAM. We do have computers now with laptops with 64 gigabytes of RAM. If you think about your smartphones, most of them are kind of in that 8 to 12 gigabytes of RAM right now. And that has more to do with just the nature of the stuff we're doing on those devices, although they're becoming more and more productivity tools than ever before. In fact, I make a bet that there's at least one of you, probably more than one of you, that's attending class today on a smartphone. You know, you're sitting on your couch with your phone in front of you and you're watching instead of a laptop, or you're in the car and you're listening to the lecture, whatever it is. You know, and I can say, you know, as an educator, these things aren't the, you know, the most efficient ways of learning. You know, but hey, you know, we're all adults. You live life the way you're going to live life. And maybe you had a doctor's appointment this morning and you're on the road and it was skip class or listen to it on the phone. That was your option. So, you know, we go through life and we make some of the best choices we can. But, you know, the point is that historically, if you couldn't physically make it to class, you'd miss class. Now we have this option for Zoom where if you're homesick, but you can physically pull yourself out of bed, or at least get your laptop near you in bed and stay awake, you can attend class via Zoom. That's a perk. You know, now we take it a step further. You could take class with you on the phone on the road. So you don't even have to like, oh, I have to leave class early to get to a doctor's appointment. No, just take class with you. It really is amazing, those decisions, those handoffs that we make with modern day computing. But, you know, you do think about if you are in a fixed space, you want a larger or fixed place, you want a larger screen, better audio, things like that. You can see the slides, you know, whatever we're currently looking at. Second, I gotta stand up for a minute. Old bones. We'll move back to seated in a few. All right, so in any case, there's kind of our cost of memory that we want to consider, cost of resources on these things. One example I like to put in my my classes is from my recollection, the first big memory upgrade I ever made in a computer. So this was something, this is in 1994. My computer had 8 megabytes of memory. Keep it, and that was super high end. So 8 megabytes of memory then was probably equivalent to like a computer with 32 gigabytes of memory today. And I decided I wanted to double my memory. So I wanted to get another 8 megabyte chip for my computer. In 1994, 8 megabytes cost $1,000. Now, what's funny is to us today, if you look up above here, by today's value, 8 megabytes is less than a penny. It's 0.0032 cents. so we'll just round up and call it 1 penny. So in 1994, I spent $1,000 on something that costs a penny today. You couldn't buy it today because of how small it is, but it would cost a penny today in terms of that amount of memory. And frankly, this maybe has come down a little bit. It's maybe even more. Maybe it's a tenth of a penny or whatever. It's worse. It keeps getting cheaper and cheaper. So what does that come down to? Well, it comes down to the difference between today we pay $0.004 per megabyte versus before we had $125 per megabyte in 1994. And this is already after memory had substantially come down in price. Memory was a lot more expensive than this prior to 1994. So just kind of a, you know, so he just needs to, you could just see how much cheaper stuff has become. Anymore, a lot of our limitations on our desktop computers is, do we have the physical memory slots to add more memory? Because it's not really expensive. You can go to Amazon and buy another 16 gigabytes of memory for, you know, $40, $50, something like that. But you need to make sure you have the physical slots on your computer's motherboard to put more memory in there. Otherwise, you're going to have to take other chips out to put the more memory in, and you're not going to, and then you're going to be left with these unused chips. For laptops, they're significantly less expandable, especially modernly. We're going to talk more about how we've moved away from things plugged into a motherboard and moved more to things being very integrated through soldering or systems on a chip. We talked a little bit about systems on a chip last class when we were looking at like the M1 processors. You know, at the high level, but now we're moving more towards something like that, where the level of expandability, the level of upgradability of our mobile devices is very low today. So basically, when you buy a mobile device, whether it's a computer or a smartphone, you're paying for all the specs you'll ever want day one. So if you think you're going to need a laptop with 32 gigabytes of memory in it, it would be in your best interest to save a little extra money to get the 32 gigabytes when you first get the laptop, rather than get 16 with the expectation you'll be able to upgrade later. That used to be a truth. It's not. It's usually not true today, especially on our higher performance laptops. Our higher performance laptops tend to be very integrated machines. And now, like I mentioned with the Mac, you know, I'm here on a MacBook Air, so I'm running an M1 processor on this particular computer. Inside my laptop here, I'm going to basically have a processor with a solid state drive soldered to it, and then batteries. That's what lives inside of this laptop, because such a high percentage of the computer now just lives right on the chip. So it becomes kind of an interesting thing. And I have a picture a little bit. Let me just jump down here. We've already talked about CPUs in terms of the brain. We already did that paper. So, you know, when you really think about what a computer looks like, you have our historical computer, we have this motherboard that all of these different things plug into. And a lot of times they're plugged into it through cables and stuff like that. And over here on the right side, this is typically the stuff that's inside of the computer, while our GPU is typically inside the computer as well. In a desktop computer, these things might be removable, but in a laptop, or certainly in a smartphone, it's in there. You're not changing it. It's going to be whatever it was the day you bought it. All right. So our design decisions for our mobile devices are moving towards, well, have already moved towards less and less upgradable. So you need to buy everything you'll ever need day one. So we already talked about this. Goals of mobile devices. We want enough storage to hold our pictures. We want enough storage to hold our music. We want lots of battery life, so it lasts all day. We want a good camera, so that might be more or less important to you depending on if you take a lot of pictures, or you take the occasional picture of a cheeseburger or something like that. Display size is something else we care about. Some of you want a smaller display, so the phone's more compact. It'll fit in your purse, you'll fit in your pocket, whatever. Other, like me, the bigger the phone, the better. I'm a big guy to begin with, so a giant phone in my hand is probably going to look like a normal phone in your hand. But outside of that, and then obviously I'll have big clothes. So a big phone fits in my pockets very easily. But outside of that, I watch a lot of videos and things like that, YouTube, on my smartphone. So I value that bigger screen, even if the phone is not as compact. Where other people, they want it to be much more mobile, easier to just, move around places, whatever. So that display size, we're starting to see multiple choices for that, especially as our battery life has gotten better. Display size is directly related to our device size. Our device size is related to display size along with the battery. So those are things that are important to us with our mobile devices. One interesting thing that I like to talk about, this is kind of more of an interesting use case. I think we did the poll maybe day one, but a pretty decent guess that roughly half the class is running iPhone and the other half of the class is running Android. Maybe it's a little bit more lopsided. I think I've probably noticed that students coming over from India are more primarily using Android. If you go ahead and throw into the chat whether you use iPhone or Android, just out of curiosity. My guess is this class will be Android heavy, but usually it's roughly 50-50. But then I'm going to tell you a secret that you maybe didn't know. Oh, we got iPhone. We're even at this point. Pretty close to even still. Yeah, yeah. So I'll come back and check on this in a little bit, but we're seeing pretty clearly here that it's basically going to be a roughly a split. Half the people are on Android, half the people are on iPhone, and that's, you can walk into any modern group of people and you're going to have a pretty similar breakdown. They're legitimate competitors now. You can't necessarily say one is definitely better than the other. It's got to be what's the right use. My wife's on an iPhone, I'm on Android. We used to both be on iPhones. I write software for both, so I run both. But the secret I'm about to tell you is actually the main reason that I stick with Android. And it comes down to our, when you create an internet hotspot. And it's a handy thing. So, you think about other uses for our mobile devices, things we're expecting out of our mobile devices. And now we effectively have an internet connection which travels with us. So, for example, yesterday I was sitting at a restaurant near here, which I think one of your classmates works here. But I was at a place called Stillhouse in Cedarburg, and they don't have open Wi-Fi if you have like a laptop or something like that in there. It's not the type of place you go and sit and work for 6 hours. It's like a restaurant or a bar type place. But I had my laptop with me because I had about a 20-minute wait till my buddy was meeting me there. And I obviously had my smartphone in my pocket. And I walked in, opened up my laptop, was going to do some grading. There was no Wi-Fi. So I just created a hotspot on my phone, hit a button, and all of a sudden I'm sharing my mobile phone's data plan with my laptop. Yeah, it worked great, no problem. I have unlimited data, so I don't have to really worry about that. It was the perfect fix for the situation, and it made something that historically would have been inconvenient. It made it a non-issue. In fact, it's common that I'm in a coffee shop or something like that, and I choose to use my personal hotspot instead of their internet. If they're very crowded or they have bad internet or something like that there, I'd rather have a stable internet connection that's faster from my smartphone than an internet connection from from a coffee shop. Another common misnomer is Wi-Fi is not necessarily, Wi-Fi doesn't say anything about the speed of internet. Wi-Fi says this is the mechanism by which the internet is delivered. The source of that internet is what dictates the speed. You can say the Wi-Fi dictates the maximum speed it can be capable of moving at, but most of our Wi-Fi technologies today are all going to be able to move faster than our internet connection speeds. It's getting closer and closer, but I think we're still going to always win. But that is a common misconception that, oh, Wi-Fi is better than my cell phone data. That's not necessarily true. In fact, in many cases today, as our cell phone data has gotten so fast, it's probably uncommon for public Wi-Fi to be faster than your cell phone data. So really the problem is you might use public Wi-Fi so that you're not using your data plan if you don't have unlimited data, or if you travel and you use data in another country, that's going to cost you extra money. I have a thing on my phone, we travel a lot, which is going to be related to this next conversation, but where if I'm in a foreign country and I connect to their cell tower with my phone, I turn off airplane mode, for example. The second I connect to their cell tower, I've committed myself to, I think it's $10 or $12 for the day. And now I have effectively my internet, my whole phone plan that I have at home, I have it in that country for that day for $10. So good deal. I get unlimited data then over in the middle of nowhere. I don't have to worry about it. Okay, so now in any case, so this internet hotspot idea, not all hotspots are created equal, is today's consumer hint. And this is a pretty interesting use case that maybe some of you will find some interesting uses for that you didn't consider. So my wife and I typically, we go on a lot of cruises. So there are these big boats in the middle of the ocean, and now cruise ships, they have internet connectivity, and it's shocking actually how good the internet's getting on these cruise ships. You're sitting out in the middle of the ocean, and currently the coolest technology is what the Royal Caribbean ships have. I mean, it's effectively you have a cable modem at sea. You're in the middle of the ocean and you can easily stream Netflix and stuff like that and download big files. It's kind of shocking. But now if you've been on a cruise before and you've looked at how much the internet costs, they charge you quite a bit. So maybe for a 1-week cruise, a unlimited internet connection for one device, one person, one device might be like $175 for a week. That's pretty expensive. Well, also now we got, it's my wife and I on the cruise ship. So she wants an internet package. I want an internet package because we're not necessarily right next to each other the whole time. Sure, you can make an argument that, oh, I'm on vacation, I should probably disconnect from the internet. But it's hard to do in today's society. So we're getting it for 2 devices. So now we're at, call it $350 for internet for the week. Well, I have my smartphone. I also have my laptop. I might be sitting at a bar somewhere and I might want to work on my laptop. And, I can, log out of the phone and log into my laptop so I can kind of play the game and make it work. But an interesting truth is, and this is something that is one of the main reasons that I don't go away from Android, because iPhone does not work this way currently. When you turn on a mobile hotspot on your iPhone, 100% of the time, what you're doing is you are sharing your cellular data plan. That's what you share when you turn on an internet hotspot on an iPhone, is your cellular data plan. Now, most of the time, that's what you want. For instance, I mentioned I was at Stilt House yesterday. I needed an internet connection so my laptop could hit the internet. I wanted my phone to share its cellular data plan. Great. But now, think about that cruise ship example. My phone is connected to the ship's Wi-Fi. I want to have my phone share the ship's Wi-Fi to my laptop. The hotspot on Android, what it does is it shares whatever internet connection you are currently on with other devices. So if that is cellular data, it shares that. If you're on another Wi-Fi connection, it shares that. So it's a pretty handy tool, or even like a Concordia. When you're on campus, you're connected to one of the Wi-Fi networks and you have to log in with your username and password and things like that. With an Android device, you can share your that internet connection with people around you by creating a hotspot on an Android device. So it's actually a pretty handy tool that comes, that's good in certain situations. That's one of those little tiny caveats between iPhone and Android. That's an important feature in my view, that Android can share whatever internet connection you're currently on, as opposed to iPhone only shares your cellular data plan. So, yeah, just an interesting thing to consider when you're comparing those 2 devices. If that's not something you run into very often, obviously that might not be a decision maker for you. But for me, it is. Okay, so you would have run into a lot of this stuff in your paper with flash memory stuff. So kind of the different evolving technologies of solid state, which is effectively flash-based technology, but increasing that communication channel between your SSD over a serial ATA cable, for example, to your motherboard. What can we do to make this SATA connection faster and faster and faster and faster? So one of the things is this NVM over a fiber connection. That's faster, and we're constantly trying to make these things faster so that we're no longer limited. So even if this guy can go at 1,000 miles an hour, if this connection only supports 500 miles an hour, you're only using half the performance of this device. So if we can get this to go faster and faster and faster, we can come closer to maximizing the full performance of our devices. Okay, so that's something you've already looked into, but that's the kind of where we are right now when comparing these various devices. Okay, so kind of keeping going down that rabbit hole, catching up to some of the papers we've done up to this point. We talked about the idea of a compiler. So if you're writing a computer program, like in a high level language, C, C++, Java, C#, and you want to turn that into something that runs natively on a computer. The idea is that so a compiler is a tool that turns a high level programming language like Java into a low level language like assembly that runs directly on the computer's hardware. And one of the things, and the reason we do that, and I have a picture here. This is an example of i386 assembly, and we're going to walk through this actually here now, either a little bit today or maybe next class. But this is a picture of a hello world program in i386 assembly. So this is not necessarily the friendliest syntax. If you were a computer programmer and this is what you had to do day in, day out, you might find that very tedious. So as computer scientists, as computer programmers, we prefer to write code, one line of code, just say like print hello world, compile it, and have it magically get turned into all this. So that's the tool that a compiler does for us. All right, so now you had a paper where we looked at why does a compiler need to know about not just our target architecture, which is the type of processor we're on, but also the operating system that we're targeting. Why does it need to know about both those things? And actually, let's go ahead and explain that through our picture here. So let's talk about these couple of slides and we'll get to it. So for example, we have two different things. We have an architecture and we have an operating system. So most of our mobile devices today are running this ARM-based computer architecture. All right, that's the language that the processor natively speaks. All right. Now, when in our world right now, when we're talking about smartphones, for example, we have two different target operating systems. We have iOS and we have Android. So even though all of these processors are speaking the same hardware-based language, that becomes a little bit fuzzy when you have like a company like Apple making its own processors because they can add some stuff in that isn't just part of the ARM core, but let's just say that they're all talking roughly the same low-level language. What does the fact that they're running iOS or Android, what does that change? And to consider that, we have to think, what does an operating system do for us? And we've already talked about this at the high level. The operating system sits between the human being, and I have this in our picture up here. The OS sits between the human and all of the computer's resources, so that we can just double click on stuff or whatever, and it handles what shows up on the monitor by going through the graphics card. It handles input from the keyboard. It handles input from the mouse. It handles moving things to and from system memory, moving things to and from the processor, getting things from the hard drive into system memory, which then feeds the processor. So it's doing all that magic of managing all of those resources for us, so that the human being up here only has to double click on stuff or drag things around or whatever to use a computer. Makes our lives a lot easier. Okay. And the way that a operating system does that today is through something called system calls. Now, let's write a slide here. It's called system calls. And I'm going to put in parentheses here an API. Okay, API is an application programming interface, sometimes as an abstract programming interface. So an API is a series of functions. In the web API world, sometimes these guys are called endpoints. So if we're just kind of using one of the classes you're going to take with me, if you are in the software engineering concentration, is the Restful API class, where we talk about this a lot. So I'm kind of trying to merge the idea of system calls with APIs, because they effectively are the same thing, just we access them maybe a little differently. So if we're talking about an operating system, there's a whole bunch of built-in functions that allow the operating system to pre-solve a lot of the hard parts of some problems. For instance, how do you get something to display on the screen? So we might have a system called Cis-Write, for example. Whereas when we're dealing with web applications where we have like a cloud-based thing, we might call upon some endpoint, which effectively will call some function up there to perform some task. All right, so this is a series of functions or endpoints which perform, I'll put it quotes, common tasks relative to the problem being solved. An OS has a collection of functions, system calls, that do OS related stuff. Basically, the OS has pre-solved many of the problems that commonly happen between the human and the hardware resources. All right, so these are like power tools. Okay, you might think like as an example, let's say a human being needs to I don't know, hammer something in. We'll just kind of using the answer with the thing, but we need to pound something into the ground or pound something into a piece of wood, something like that. Well, if we go back before our tools, what did a human being have to do? They had to go and find something. Maybe they had to find a rock that they could use to swing down and hit the thing and stuff like that. But what did human beings do? We invented a hammer that was specifically designed for the job of driving something into something else. Okay, so we can think of that hammer as kind of being like a system call. We can use that hammer anytime we need to drive something into something else. All right, so that's kind of our real life example of something like that. So our operating system is going to have a collection of things like that that allows us to do computer resource related types of things. And let me just see where the next slide. Okay, yeah. So I'm going to finish this conversation today. Okay, so just to give you an idea of that. So we're going to look at this Hello World Linux assembly program. And some of you have seen this before in my classes because we look at stuff through different angles. But if we were not targeting an operating system, and we see here on the very next slide, what if we don't have a target OS? So we'll talk about that. But if we were not targeting a specific operating system, we would have to write all of the assembly code, all of the for mobile, all the ARM-based assembly code to directly talk to all of the computer resources. We'd have to talk directly to the graphics card. We'd have to talk directly to the processor, to the hardware registers, to system memory, to hard drive. We'd have to do all that heavy lifting ourselves for this one specific application. And then the next time we wrote an application that did some similar things, we'd have to write it again. So even though when we look at this code here at a glance, it looks fairly cryptic, it's actually leveraging a lot of power tools that are built into the operating system. All right, so in this particular example, we are looking at the i386 computer architecture. So this is the architecture you'd find in like a Intel Core i7, Core i5 processor and earlier. And we're looking at it for the Linux-based operating system. Okay, this gets back to that paper you wrote talking about why do we need to target both an architecture and an operating system. Okay, so we're going to walk through this and we're going to see the cadence of how assembly code typically works. How do computers actually, how do applications actually run on computers under the hood? So these first four statements here, these are all move statements. So what a move is, and if you remember when we first talked about processors, I mentioned, think of a processor, a CPU, as like a collection of magic tricks. And I did the thing, well, how many of you can, move your hand like this? How many of you can do this? Nobody's individually impressed with those couple of little stupid moves. But if you put them together in a sequence, you can pick up your coffee mug. For example, you can solve real problems by putting together a whole bunch of simple little movements, simple little magic tricks that I like to call them. All right. So the move magic trick, that lets you take one thing and put it someplace else. So you're taking a thing and placing it in another thing. All right, that's all move does. Now we'll just glance down here at the bottom. So we have a data section here where we're remembering that I mentioned this program just prints hello world to the screen. So we're keeping track of two different pieces of information. We're remembering two things. We're remembering what we want to display, hello world, and then we're also remembering the length of hello world, the number of characters. Okay. So those are the two pieces of information that we are remembering. So this very first line, and really these four lines can happen in any order. It doesn't really matter because the cadence here is what we do is we set up our processor. We throw into the very specific places the pieces of information that will be needed when we call upon the system call. So I just need to get into this register called EDX. This is a little storage location on the processor. I'm going to put how long the string is going to be in there. Then in ECX, I'm going to put the memory address of where the beginning of our string hello world lives. Then in EBX, I'm going to put the number 1. And in this case, the number 1 relates to where am I going to write this? So if I want to have it go out to the monitor, that's standard output. If I wanted it to write to the internet, that would be a different output stream or something like that. But 1 in Linux is the thing that's linked to standard output. All right. And this last one is which system call am I going to want to call? We haven't called it yet, but I'm going to put inside EAX the number 4, and 4 happens to be the system call for syswrite. And syswrite is the function that lives inside of Linux, the system call that lives inside of Linux that has been pre-written that knows how to display some message of some length to some output stream. All right, so those 3 pieces of information, what is it, how long is it, and where do you want me to write it? Those are the 3 pieces of information that syswrite needs in order to function. So all I have to do is I stage these 4 memory locations, these 4 hardware registers with the correct information. So these 4 lines can be in any order that we want, doesn't matter. But they do need to all get filled up before we do this next magic trick. The next magic trick interrupts the current process. So tells the CPU to halt and turns the control over to our operating system. So we're calling the kernel. So if I pretend like I'm Linux and the CPU just waved the flag at me and said, hey, it's your turn, then I know, okay, it's time to go. What am I going to do? I'm going to go ahead and I'm going to go and check inside of EAX and find out, well, did the user have something they wanted me to accomplish? And I find the number 4 in there and say, oh, they want me to do a syswrite. Okay, Well, since I'm going to do a syswrite, I'm going to need 3 pieces of information. I happen to know, so somewhere it's going to be documented, that those 3 pieces of information are going to be in EBX, CX, and DX. So I'm going to go and look in EBX to find out, well, where does the user want me to write it? Then I'm going to go into ECX and find out, okay, where in memory does the thing they want me to write begin? And then I'm going to go into EDX and find out, well, how many bytes starting at that place in memory do they want me to write? And then I'm going to do my magic trick. I'm going to spit hello world out to the monitor, because that's what syswrite does with these 3 pieces of information. All right. So these 5 lines ultimately get hello world on the screen, leveraging this system call from the operating system. So even though this is assembly code, this is the low-level code that a processor understands, this code is not that useful unless it's relying on an operating system that is taking advantage of it. Okay. Now, down here, we notice that we go ahead and set the exit code inside of EBX to 0. And then we change the thing we want to do. So EAX used to be a 4. That means we wanted to do a syswrite. Now we're changing EAX to a 1 because we want to do a Cis Exit. And a Cis Exit is a different system call. And what it knows how to do is kill the current program. And when the program ends, it can spit out a value, an exit code that says whether or not things went okay. So in order to, so the one piece of information Cis Exit needs here is some exit code, some number that's going to go inside of EBX. And then what do? We interrupt again and tell the operating system to take over. What does the operating system do? They do the identical thing to what they did last time. They first go and look at EAX and say, what do you want me to do? You want me to do magic trick number 1. Okay, so you want me to do an exit. Fine. So I'm going to say, oh, well, for doing an exit, I need to know, do you want me to let the user who called this program know about any sort of special exit code? 0 means everything went fine typically. And then it will just perform that exit code. And then this program will end because that's what the operating system does when Cis Exit gets called. So that is hello world for Linux in assembly language using Linux system calls. So that's using a whole bunch of power tools. If I didn't have syswrite, I'd have to put all the assembly in here to accomplish whatever syswrite does. If I didn't have sysexit, I'd have to have all the assembly code in here that accomplishes the same thing that sysexit does. So some smart people who wrote that Linux operating system did all that work for us so that we didn't have to. All right. So what I'm getting at here is, yes, this is assembly code, but it could be a lot worse. And that's the reason why our compilers require us to target both an architecture, the kind of processor that the program's going to run on. So we use the right instructions. So we use like move and int for interrupt, that kind of stuff, as well as what operating system are we going to be talking to, so that we can take advantage of any power tools that the operating system provides for us, so that we don't have to output all of that assembly for us. So here's kind of the picture for that. What if we don't have a target operating system? Okay, if we don't have a target operating system, then the default target would be something called the BIOS. So, you know, this is the basic IO system. So when you first turn your computer on, before it starts loading Windows or loading the Mac OS or loading Linux, you got some stuff that shows up on the screen. So on your motherboard, there's actually a tiny little basic operating system that knows how to talk to all your different resources at the very basic level. So we don't have any of those power tools built in. And because of that, if you were writing code that runs directly on the processor through the BIOS, you would have to write all of those details. So imagine if you're the person who's writing an operating system. So now we're talking kind of a chicken or the egg issue. If you're writing an operating system, the operating system you would be targeting initially is the BIOS. So what you actually do is you write the first part of your operating system. Typically it's called like a bootstrap. You write the first part of your operating system to work with the BIOS to ultimately launch your larger operating system. And what you would initially do is you would launch into memory kind of a basic but more capable software-based operating system that allows you to do some of the other heavy lifting that you want your ultimate operating system to do. So you kind of go in layers. You go from the least or from the most complex, that's just sitting there talking directly to your hardware, to one level up where, hey, it's less complex than that, but still only so usable, to then you start adding all these extra power tools into it and things like that. Okay. So that's what would happen if we did not have a target operating system, which would make writing assembly code even less fun for us, which is the punchline here. So just to kind of wrap up that conversation, you know, when we say computer architecture, what are we actually talking about? We are talking about that instruction set that the CPU understands, and all the different things that might work with it to accomplish a task. Okay. We've pretty much already talked about this stuff. So, you know, we do have different decision making that goes into these different architectures, you know, depending on, you know, the amount of power, the heat, all that stuff. So those are the things that drive the architectures we might use. And I mentioned earlier that most of our modern mobile devices are using an architecture based in something called ARM, which has been widely adopted and has been mostly designed around our mobile devices because it tends to be lower powered. It was designed for mobile in mind. So it made some of the decisions that it made on that processor to be friendly on battery life, power consumption, things like that, potentially at the cost of performance. All right, so at this point, we typically are not viewing the ARM processors that are inside of our smartphones as things that are as powerful as our Core i7 processor in our desktop. But they're not supposed to be as powerful because the trade-off is you get better battery life and all this other stuff, but they're powerful enough. That's kind of our punchline. All right, we've talked about that. Okay, so I'm gonna start here next class. So just to give you a little preview where we're going, we're gonna start talking about the things inside our computer. I think I had already what I'm going to do. So I already have homework 4 unlocked for comparing and contrasting iOS versus Android. We talked about like the hotspot thing today. I'm going to go ahead and unlock homework 5, which talks about the uses of binary, octal, decimal, and hexadecimal in modern computing for you to look into that. Because that's going to be stuff that we are going to start dealing with as we look at some examples in ARM assembly. Yeah, I think that gets you far enough down the line for now. Let me quickly here make sure that let's So the ARM processor assignment was due today. Okay. Let's see when our next one. So iOS assignment. Is due next class. And then we're going to have this binary one. Due on the 5th. Next week. Click. Oh, just taking time. Okay, so I'll make sure that gets saved. Okay, there we go. So I'll see everybody on Thursday morning. Questions, comments, concerns, bribes. Okay, well, I will see everybody on Thursday.
Thank you and bye.
Professor.
Thank you. Bye, Professor.
Thank you.
See you, Professor.
Have a good day.
Hey, you take care.
Hello, Professor.
Hey.
This is Gayatri.
Yep.